This is Precalculus. We're in chapter 8 on lesson 3. I want to start on page 540. So go ahead and turn your textbooks to page 540 to the chart near the bottom of the page. But let's remind ourselves where we've been. Okay, we're in trig. And lesson 1, we dealt with solving trig equations graphically, so we graph them on our calculators. In lesson 2, we learned that when we look at the inverse of a trig function, we have to limit the domain because there are repeat. The inverse is not a function if you do not limit the domain. All right. I also want to remind us of how the graphs look. Remember, the sign begins at 0, goes up to 1 at pi over 2, goes back to 0 at pi, goes down to -1 at 3 pi over 2, and back to 0 at 2 pi. All right. So on the sine curve, in one cycle, there's only one value where the sine of an angle equals 1, right? There's only one radian measure. The same is true for -1. So this would be, like in our quadrants, this would be quadrant 1 between 0 and pi over 2. This would be quadrant 2 between pi over 2 and pi. This part would be quadrant 3 between pi and 3 pi over 2. And this would be quadrant 4 between 3 pi over 2 and 2 pi. All right? So let's just think when we limit the domain for the sine, we look at quadrants 1 and quadrant 4, all right? So that the inverse is actually a function, all right? But when we are looking, so this is a sine curve, right? So when we are looking at the curve, quadrants 1 and quadrants 2, if I'm looking for an angle such as a radian, like pi over 4, you know that the sine of pi over 4 is square root of 2 over 2, right? It is also the square root of 2 over 2, it's that ratio that the sine of 3 pi over 4, 3/4 pi, right? So within one cycle, there are two values that have the same output, the same y value, right? So pi over 4, and this would be square root of 2 over 2. Pi over 4 is equal to square root of 2 over 2, and the sine of 3 pi over 4 is also equal to square root of 2 over 2. All right, so when we are looking at the sine curve, then we need to remind ourselves that if we're talking about a positive value, we need to be looking in quadrants 1 and 2. And that one of our identities says that the sine of any radians equals the sine of pi minus those radians. Okay, so let's take pi over 4. We just agreed that the output for the sine of pi over 4 square root of 2, the same as the sine of 3 pi over 4 is the square root of 2 over 2. So that's the same thing as saying the sine of pi over 4 equals the sine of pi minus that x value, pi over 4. Well, what's pi minus 1/4 of a pi? It's 3/4 of a pi. So when we are solving for all the possible values of the sine of any angle. Because remember, there are an infinite number of solutions for the sine of some radians equals the square root of 2 over 2. Remember, there are an infinite number of solutions because this graph is cyclical. It repeats over and over and over again, such that it repeats at every 2 pi, because that is the standard period for a sine. And we did this last semester in the previous chapter. We looked at all the possible solutions, and the distance between one solution to the next was 2k pi. Remember when we did that, right? All right, but within one cycle, there are 2 solutions for this. All right, so when we're solving for this, we have to realize that we have multiple solutions, infinite numbers of solutions. And there are 2 within one cycle. Now, what's also important is, let's say square root of 2 over 2 wasn't on the unit circle, and we wanted to use our calculators. So when we did the inverse square root of 2 over 2, what am I doing? I'm limiting the domain. And it is only going to look at quadrants 1 and 4. In this case, because the ratio is positive, we know it's going to be looking in quadrant 1. But because it's a sine curve, I know that there's a positive ratio in quadrant 1 and there's a positive ratio in quadrant 2. Remember, all students take calculus, right? We're looking at our quadrants. All students take calculus. First and second quadrant, the sign is positive, that ratio. But when I put it in my calculator, I have to remind myself, and the only time we're putting this in our calculator is when that ratio is not on the unit circle. So when it's not 0, 1, -1, 1/2, square root of 2 over 2, and square root of 3 over 2, right? Those are our ratios that are on the unit circle. When it's not one of those ratios, and we have to use the inverse function to solve for the radians, we have to remind ourselves that the sine of any radians is equal to the sine of pi minus the radians. We're going to walk through some examples, all right? So sine, positive in first and second, negative in third and fourth, but when we use the inverse, we're limiting the domain to the fourth and the first quadrants, all right? Now cosine. Let's remind ourselves, all right, I'm going to leave this here on the board so we remind ourselves as we're working through the problems. Let's think of the cosine curve. All right, the cosine curve starts at 1, at 0 radians, right? It's 0 when we hit pi over 2. It goes down to -1 at pi, goes back up to 0 at 3/4 pi, and up to 1 at 2 pi. All right, so this is pi over 2. This is pi. This is 3 pi. It's 3 pi over 2. I've been saying 3 pi over 4. It's 3 pi over 2. Well, maybe that's what I've been saying. It's 3 pi over 2. 3/2 pi. All the way to 2 pi. Go up to 1, down to -1, right? So this is the cosine. Such that this is quadrant 1 between 0 and pi over 2. Between pi over 2 and pi, it's quadrant 2. Between pi and 3 pi over 2, it's quadrant 3. And 3 pi over 2 to 2 pi, it's quadrant 4. All right, when we limit the domain on the cosine, what quadrants are we looking at? For the sine, remember, quadrant 1, quadrant 4. For the cosine, we're only going to limit it to quadrant 1 and quadrant 2 because its inverse is a function. Because remember, the horizontal line test is what tells us whether or not the inverse is a function. All right. So sine, what quadrants are in? We're in quadrant 1 and quadrant 4 when we look at the inverse. The cosine, we're in quadrants 1 and quadrant 2. All right. And just like the sine curve. In one cycle, the ratio 1 for the cosine of radians is only 1 at one point. It's only -1 at one point on that curve. All right. It is 0 at 2 points, and the distance is pi between that, right? All right. So because we're in quadrants 1 and quadrant 4, if I were to say, let's say the cosine of pi over 4, you know, is the square root of 2 over 2. So you just want to look at where else on this curve, what other radian measure is the ratio of the cosine square root of 2 over 2? Well, you know you have to go to the fourth quadrant because all students take calculus. First quadrant and the fourth quadrant is where the cosine is positive. So actually, if you go backwards on the curve, right, to the left of the y-axis, then we're in quadrant 4, and those are negative angles, right? Such that the cosine of pi over 4, that equals the cosine of negative pi over 4, right? So if this is pi over 4 here, that's the square root of 2 over 2. Negative pi over 4, because those are negative angles because we're rotating it clockwise, is also square root of 2 over 2. All right, so even though with our inverse, we're looking at quadrants 1 and 2, when we solve for all the possible solutions of the radians, for the radians for an equation, a trig equation, I'm going to go forward to quadrant 1 and back to quadrant 4, such that the cosine of any angle is the equivalent of the cosine of the opposite of that angle, right? All right, so this lesson, we're going to use these concepts to no longer solve the trig equations using our calculators. We're going to solve them algebraically. Okay, wait, I need to say one more thing. The trig function. Because the trig function, we didn't have to limit the domain because from quadrants 1 through 4, because of the curve, right? I'll just draw it. Remind us, right? There are the asymptotes for the tangent at every odd half pi. So at negative pi over 2 and at positive pi over 2, there are the asymptotes. So that this passes the horizontal line test. One cycle passes the horizontal line test. So we don't have to limit the domain when we take the inverse of the tan. There's always only going to be one solution for the tan, and its cycle is going to be 2 pi. So if I were to ask you, what are the radians where the tan is 1? We know the tan is equal to the sine over the cosine. In order for it to, that ratio to equal 1, the sine and the cosine have to be the exact same measure, right? The ratio. And that only happens at pi over 4. And so the radians would have to be pi over 4. And it would be plus and minus k pi, right? Because one cycle of the tan is pi. One period of the standard tan curve is pi. So tan is only going to have one solution. So you don't have to think of this, either one of these concepts for the tangent. The tan of x, you're just going to solve for. All right? Now, okay. Let's walk through the examples. Example 1. So I'm on page 538. Example 1. We're going to solve this equation. Cosine x equals 0.6. All right. 0.6 is not on the unit circle. That's 6/10, right? That is not on the unit circle. So we have to use our calculators. And we have to use the inverse cosine function. So we use the inverse of the ratio equals the radians. When I do the inverse, what am I doing? I'm only looking at quadrants 1 and 2. In this case, because the ratio is positive, I'm in quadrant 1. So this in my calculator is only going to give me the solution in quadrant 1. But I know that there's another solution in quadrant 4. So the first thing I'm going to do is solve for the solution in quadrant 1. Let's make sure our calculators, that they are in radian mode. All right, I was making sure mine was. And we do second cosine 0.6 equals, all right, that's what I did in my calculator. So that gives me the radians. All right, so x equals, oops, I picked up the wrong thing. 0.9273. 9273. Remember the standard for trig is 4 decimal places, so I rounded this 2 to a 3. All right, well, that is one solution, right? And it is plus minus 2k pi. That's one solution. But I'm going to apply this because, okay, all right, let's think about this. Is 0.923, what quadrant is that in? Okay, we're not used to seeing radians written as a decimal. But radians, like pi, is really just 3.14 and on and on and on, right? It really is a value. This value is in quadrant 1 because quadrant 1 goes from 0 to half a pi. Well, if pi is 3.14, then half a pi is 1.57, right? About. So it is between 0 and 1.57. That is in quadrant 1. Well, I know that there's also a value in quadrant 4 because the cosine is positive in quadrant 4. All right, so how do I calculate the value of x? Well, I'm going to use this. The cosine of x is the cosine of the opposite of x. So really, I don't even need my calculator for this. Another solution for x is negative 0.9273 plus minus 2k pi. All right, so for the cosine, well, tangent's the easiest, right? It's just one value, plus minus k pi. The cosine is the second easiest. It's just plus minus the same radians, all right? The sign is going to be different. All right, let's get example 2 on page 539. We're going to solve the sine of x is negative 0.75. All right, that's 3/4, negative 3/4. That ratio is not on the unit circle. If it's on the unit circle, I'm not using my calculator. I'm remembering the radians that go with that ratio, all right? When it's not on the unit circle, I have to use the inverse function. When I take the inverse function of the sine, what quadrants am I limited to? 1 and 4. All right, so the inverse sine of that ratio, negative 0.75, is going to equal x. Because that's a negative value, what quadrant is it going to give me the solution for? Quadrant 4. All right, I just put this in my calculator. I have to go back and find the solution for quadrant 3, because the sign is also negative in quadrant 3. All right, so I do the same. Shift sign, negative 0.75. I get my radians, and it gives me a negative angle. So x is negative 0.8481. All right. Well, that's the 4th quadrant, and that's rotating right clockwise. And that's okay, because negative 0.841 is in fact in the 4th quadrant, but I need the one in the 3rd quadrant. I'm just going to use that the sine of x equals the sine of pi minus x. So I'm going to take pi minus this value. All right, so pi minus negative 0.8481, and that is going to give me the other solution. Okay, pi is second and your caret top button. Minus the negative is positive, so I'm going to add it, 0.8481. All right, so x, and this is plus minus 2k pi because of the cyclical nature of the trig curves. So it's 3.9897 plus minus 2k pi. So I have both of those solutions. All right, now we'll do one for the tan. Remember, how many solutions does the tan have for any ratio? One. And the distance to the next one is just k pi. All right. So example 3, on the top of page 540, is the tan of x equals 3. 3 is not on the unit circle, so I know I have to use my calculator. I'm going to use inverse operations with the tan. I'm just always with the tan looking at quadrants 1 and 4. So when I take the inverse, I'm still looking at quadrants 1 and 4. So the inverse of the ratio equals the radians. And I do that in my calculator. Second tan, 3. And I get my radians. Okay, what quadrant are we expecting 3 to be in? The 1st quadrant, right? Yes, the 1st quadrant. Hopefully you got that right. So it's 1.2490, and it's going to repeat every k pi. So plus, minus, k pi. K being a constant, any value, right? All right, those are the basic equations. Now we're going to get more complex. All right, so an example 4 on page 541. All right, now it's not simply a trig term of radians equals ratio. We're going to add and subtract different numbers. Okay, so the equations are going to be more complex, but we're going to simplify them. All right? So look at example 4. It's 8 times the cosine of x minus 1 equals 0. Well, I just want to solve for the cosine of x, and I'm going to use algebra to do it. I move the 1 over first through addition. So 8 cosine of x equals positive 1. Then I'm going to divide both sides by 8. So I have the cosine of x equals 1/8. 1/8 is not on the unit circle, so I'm going to use my calculator, remembering when I do the inverse operation of the ratio, I'm limiting the domain to quadrants 1 and 2. Because it's positive, I'm going to have a quadrant 1 solution. For the cosine, it's both that positive and the negative radians. So I just do second cosine, 1/8, and I get my radians equals the value of x, the radians. X equals 1.4455 plus minus 2 k pi. And because we're going to do the positive and negative cosine, x equals negative 1.4455 plus minus 2 k pi. All right. Now look at example 5. We have the sine of u. They changed it to u because this one's going to be on the unit circle, equals square root of 2 over 2. All right, we know that ratio is on the unit circle. So I'm not using my calculator. I already know that u is pi over 4 plus minus 2k pi. It's also going to be in that second quadrant, or it's pi minus this value, and u is 3 pi over 4 plus minus 2k pi. All right? I'm not using my calculator when that ratio is on the unit circle. Okay, look at example 6. Now all we did was, it's the sine of 2x. So my radian measure is 2x. I still know that this ratio is on the unit circle. So I'm going to say 2x equals u, and I'm just going to solve for u. Well, I just did, right? U is pi over 4 plus minus 2k pi, and u is 3 pi over 4 plus minus 2k pi. All right, because I set u equal to 2x, I solve for u. Now I'm going to go back in, and for u, I'm going to put 2x. So 2x is pi over 4 plus minus 2k pi, and 2x is 3 pi over 4 plus minus 2k pi. And I want to solve for x. I don't want to know what 2x is. I want to solve for x. I just have to divide every term by 2. But since we have pi over 4, I'm probably going to multiply every term by 1/2. So 1/2, 1/2, 1/2, right? That's the rules of algebra. So the 2 cancels here. The value of x is pi over 8 plus minus k pi. Makes sense? This is very similar to when we had a 4th degree, 2nd degree, and a constant, and we factored it. And we said u equals x squared, and then we had to go back in and substitute x squared. It's very similar to that. Again, this other one I'm going to multiply every term by 1/2. All right, so then we have x equals, this is going to be 3 pi over 8 plus minus k pi. All right. Now, let's move to example 7. Bottom of page 542. Now we're going to use algebra techniques to solve. These are not new techniques. All right, here's what you have to remember. Remember, the ratio for the sign is never greater than 1, never less than -1. We have to keep that in mind. All right, so look at example 7. It's 3 sine squared x minus the sine of x minus 2 equals 0. All right, I am going to just say that the sine of x equals u. I'm going to use substitution because this looks like a quadratic, something squared, something with the first power, and a constant. All right, so this becomes 3u squared minus u minus 2 equals 0. And this is probably easily factored. Remember, we want factors of -6, such that we add them together, the result is -1. So that's going to be -3, +2. Remember, we put it over 3u, over 3u. Simplify. So my factors are u minus 1 times 3u plus 2. And there equals 0, right? So then you set each factor equal to 0. So u minus 1 equals 0, and 3u plus 2 equals 0. So I'm going to add the 1. U equals 1. I'm going to subtract the 2. 3u equals -2. Then I'll divide by 3. U equals -2 thirds. All right, so I have values for u. They are between 1 and -1. So I can use them both. All right, so I'm expecting to have possibly 4 solutions at this point. All right. So now for u, I'm going to go back in and substitute in the sine of x. I'm going to erase this part. So now I have the sine of x equals 1. Well, I know there's only one solution for that. And then I have the sine of x is -2 thirds. So there's 2 solutions for this one. All right, this one is on the unit circle. Where does the sine equal 1? It's at pi over 2, right? The sine starts at 0, goes up to 1 at pi over 2. So here x equals pi over 2 plus minus 2k pi. All right, so one solution there. And maybe it just said solve in the interval. I wanted the interval between -pi. Here we go. I need to look at the interval. It said solve this for the interval of -pi, and it's inclusive, -pi to +pi. So I don't need this plus minus 2k pi. All right, so x equals pi over 2. That is between those values. So that's like -3.14 and +3.14. I'm keeping that in my brain, right? For this one, I'm going to use my calculator because -2 thirds is not on the unit circle. So I use inverse operation, remembering that I'm limiting myself to quadrants 1 and 4. Because it's negative, I'm in quadrant 4. So there's got to be one in quadrant 3. So I'll do inverse sine, -2 thirds equals x. I'm going to do that in my calculator. shift sign, negative 2/3, and I get negative 0.7, right? So get x equals negative 0.7297. We're with the sign, so the sign of any number of radians, any value of radians equals the sign of pi minus those radians. So I'm going to take pi and subtract this. All right, so there's one solution. There's two solutions because that fits our range. All right, so x can also equal pi minus negative 0.7297, and we have to make sure that that fits in our range. So I'm going to do pi minus that previous answer, and I get 2.29. That's less than pi. So this is x equals 2.2925. Final three answers. All right. Now, let's look at example 8. All right, example 8. Okay, guys, now we're going to have to use we're still going to factor, and we're also possibly using some substitution. All right, so now we want to solve the tan of x cosine squared x equals the tan x. All right. Let's subtract the tan of x and set it equal to 0. That's what you want to do. You want to subtract and set it equal to 0. So the tan of x cosine squared x minus the tan of x equals 0. I have a common term in both of those terms on the left-hand side of the equal sign. So I'm going to factor it out. I'm going to factor out the tan. So the tan of x times the cosine squared x minus 1 equals 0. Well, if either one of these terms is 0, then the result is going to be 0. So I set both of them equal to 0. Tan of x is 0. Cosine squared x minus 1 equals 0. Well, we know where the tan of x equals 0. Those radians, are we limiting our range? We have not limited our range. So we want to know all of the answers. Well, we know that this answer is x equals 0 plus minus k pi. All right, for this one I need to do some algebra. So I'm going to add 1 to both sides. So the cosine squared x equals 1. I'm going to take the square root of both sides. Realizing that on the right-hand side, it's both plus and minus. Well, the square root of 1 is 1. All right, so this is the cosine of x equals 1, and the cosine of x is negative 1. All right, these are on the unit circle, so we can know these. Remember, the cosine starts at 1, so that is 0, right? So x equals 0 plus minus 2k pi, not 2 pi k, 2k pi, and it's negative 1 at, do you remember? At pi. So x is pi plus minus 2k pi. Well, do you see any crossover in any of these? This one, this solution covers all of these. It covers 0 plus minus 2k pi because it's every pi, all right? It also covers at pi because at 0 plus, if k were 1, we're at pi. So really, this solution covers all three. So you only need this one answer. It covers all three possibilities, all right? Now in example 9. We are going to use identities. And how do I know that I'm going to use identities? All right, look at the equation. Negative 10 cosine squared x. I'm on example 9, page 544. Negative 10 cosine squared x minus 3 sine of x plus 9 equals 0. Here's how I know. I have both the cosine and the sine in one equation. I can't solve it. I need like terms. I need, I can't have 3x squared plus y minus 2 equals 0, right? I just need all x's are all the same term on one side of the equal sign. But I know that there's a Pythagorean identity with the sine and the cosine. Do you remember it? It's the sine squared x plus the cosine squared x equals 1. Well, because this is the sine, I'm going to solve this one for the sine and then substitute, for the cosine, and then substitute the sine in. So I'm going to subtract the sine squared on both sides. So the cosine squared x is 1 minus the sine squared x. This is what I'm going to substitute in for cosine. All right? So we have negative 10, and it's 1 minus the sine squared x minus 3 sine x plus 9 equals 0. All right, I'll distribute the negative 10. So we have negative 10 plus 10 sine squared x minus 3 sine x plus 9 equals 0. Now I'm going to simplify. I'm going to combine the negative 10 and the positive 9. I end up with 10 sine squared x minus 3 sine of x minus 1 equals 0. Now, looks like quadratic, right? You should be thinking it looks like quadratic. All right? So for the sine of x, I'm going to substitute in u. And then I'll go back and substitute it back in. All right, so this is 10u squared minus 3u minus 1 equals 0. There aren't factors of negative 10 such that we add them and they're negative 3. Yes, there are. Factors of negative 10 such that we add them and the result is negative 3. It's 5 and 2. And the 5 has got to be negative. Right? All right, then we put that over 10u over 10u. We simplify, that becomes 1, that becomes 2. This becomes 1, this becomes 5. You with me? This is factoring back from algebra 2. So we have 2u minus 1 times 5u plus 1. All right, that's my factors. Now for u, I'm going to go back and substitute in the sine of x and set them equal to 0. So I have 2 sine of x minus 1 equals 0. And then I have 5 sine of x plus 1 equals 0. Now, I'm just doing the algebra and solving for x, for the sine of x. So I'm going to add 1, 2 sine x equals 1, divide by 2. Sine x is 1/2. That's on the unit circle. I'm reminding myself. I'm going to erase this part. If you couldn't factor this, remember you can use the quadratic. All right, subtracting 1, 5 Sine of x is negative 1. Sine of x is negative 1/5. For this one, I'm going to have to use my calculator, all right? But I know where the sine is 1/2. Remember, it starts at 0 and counts up, all right? So from 0 counting up, that's going to be that first radian measure, which is pi over 6. All right, so x is going to be pi over 6 plus minus 2k pi. And there's 1 in quadrant 2. So it's pi minus pi over 6. So that's 5 pi over 6. And x is 5 pi over 6 plus minus 2k pi. All right, so here's the two solutions for that first factor. For the second factor, I must use my calculator. All right, so I'll do inverse sine of negative 1/5 equals x. All right, so I do second sine negative 1/5, and I have x equals negative 0.2014, and that's going to be plus minus 2k pi. And then I'm going to do this minus, pi minus that. So it'll be pi minus a negative, which is positive. So I'm going to really do pi plus. So this also equals pi. I'll just do pi minus the negative. Negative 0.2014. Okay, that's not right. Let's do pi plus, should be like 3 point something. My calculator isn't adding right. It's so strange. Look, when I did the minus and negative, that's just so strange. All right, so I'm glad I realized that's wrong. 3.3430 plus minus 2k pi. All right, so you're engaging your brain. When my calculator gave me a wrong answer, that's just so weird. Make sure you're engaging your brain. All right. Last example. We're also going to have to use identities. The identities I've written are on page 460, but remember I gave you the handout. All right, last one. All right. Secant squared x plus 5 tan x is negative 2. All right, there is a Pythagorean identity with a secant. And the secant squared x equals 1 plus the tan squared x. So for secant squared x, I'm going to substitute in 1 plus tan squared x plus 5 tan x. I'm going to move that 2 over, tan x. So I'm going to add the 2, set it equal to 0. I'm going to combine like terms. 1 and 2 is plus 3. So this is tan squared x plus 5 tan x equals 3. Now remember, the tan can be greater than 1 and less than negative 1. I can't think of factors of 3 that add to 5. So I'm going to use quadratic. For tan x, I'm going to substitute in u. So this is u squared plus 5u plus 3 equals 0. So what does u equal? U equals plus minus plus, no, the opposite of b, negative 5 plus minus the square root of b squared, that's 25, minus 4ac all over 2a. So that's 12. 25 minus 12 is 13. Am I really going to have a radical? Yes. So u is negative 5 plus minus the square root of 13 over 2. I'm actually going to put that in a decimal. All right. So we'll do the plus. -5 plus square root 13 divided by 2. So the plus is u equals -0.6972. Now I'll do the minus. -5 minus square root of 13 divided by 2. U is -4.3028. All right, so now I'm going to substitute, make u the tan of x. So here I have the tan of x is -0.6972. I'm going to leave some space. I'll write this one down here. And I have the tan of x is -4.3028. Remember the tan, I'm just going to use the inverse. We don't have to limit the domain. So I'll just do inverse tan of -0.6972 is x. I'll do that on my calculator. Here, x equals -0.6088 plus minus k pi. Plus minus k pi. All right, so that's one solution. For this one, I'll do inverse tan, -4.3028 equals x. Inverse tan, -4.3028, and it's 1.3424. So x equals -1.3424 plus minus k pi. All right, it's a tough lesson. It's a long lesson. All right, you're going to have to look at your trig identities. You're going to have to think of factoring. You're going to have to remember you're limiting the domain for the sine and the cosine. You have to remember your unit circle. There's lots to remember. We are really building upon the foundation we laid at the end of last semester.